So recall when I introduced proof by contradiction, I said that it comes in a couple of different flavors. And one flavor we still have up here is a proof of contradiction of just a single statement P. What about trying to use a proof by contradiction with an implication? So if you had a statement like P implies Q, well, to then do a proof by contradiction, you would proceed as follows. So it proceeds in the following way. We first off assume that P is true and not Q is true. So we assume that P and not Q are true, then we derive a contradiction. And that allows us to conclude that P implies Q is true. Now this kind of might seem like magic, right? How does assuming P and not Q and then deriving a contradiction lead to us being able to conclude that P implies Q is true? So I want to know specifically, how does this work? How is it a valid proof technique? By assuming P and not Q are true, and then deriving a contradiction allows us to make that conclusion. Well, it actually turns out that this proof by contradiction of an implication really is just a special case of this proof of contradiction flavor. And we already saw, using a truth table, why this is a valid proof technique. So what I'm going to do is I'm going to change my notation just slightly, because here I have P's and there I have P's and it can get a little confusing. So I'm going to erase these P's. And replace them with a different letter. So let's use, well, I have a P, a Q, let's use R. So it's the same exact proof technique, I've just replaced my letter. Instead of using P, I am now using R. So here, what I'm trying to prove is a statement P implies Q. You can think of that as an implication, or you could think of that as just a single statement. So let's let R stand for P implies Q. And let's just apply our original proof by contradiction technique to this statement R. So if I wanted to apply this proof technique to that statement R, it says I have to first off assume the negation of it. So applying this flavor 1, we have to assume not R. Well, not R is the same thing as not this implication. And we already know how to negate this implication. We go back to our logical operators and the definition of this implication. This is logically equivalent to not P or Q. And then I can apply De Morgan's law to bring this not inside this or statement, this disjunctive statement. So I have a not P, so that's going to be P. I flip my or to an and I get not Q. So with this proof by contradiction technique 1 right here, I had to assume not R. Well, if R was my implication, you notice that that is exactly logically equivalent to P and not Q. P and not Q. So all we're doing for this different flavor of a proof technique using an implication is going back to this flavor of a proof technique, and instead of treating this as an implication, we treat it as just a single statement. And then after we negate it, we end up and we find that, oh, assuming not R is the same thing as assuming P and not Q. So then deriving a contradiction allows us to then conclude that our statement, our implication, is then true. So this second flavor of a proof technique, when you apply it to an implication, is really just the same thing as this proof technique flavor, simply applied to the statement P implies Q. However, both the Book of Proof and Rosen draw it out as kind of a separate special case. And so it's a good thing to know that for an implication, if you want to proceed by contradiction, what you're going to have to be looking at is P and not Q. That's what you assume to be true.